All right, let's just jump right into it. What if I told you we could make things float with just sound? I know, it sounds like something straight out of a sci-fi movie, right? But today we're going to look at how this is actually becoming a reality. And no, it's not magic. We're talking about pure physics.
I mean, just let that sink in for a second. Floating factories. Places where tiny, delicate components just assemble themselves right there in midair. You got to wrap your head around that. This isn't some far-off future idea. This is the absolute cutting edge of engineering, and it's happening as we speak.
So the question is, how is any of this even possible, right? I mean, how can something as simple and invisible as a sound wave actually defy gravity and build stuff? Well, stick around because that's exactly what we're going to break down right now.
All right, so first up, this is not magic, it's physics. To really get how we got here, we need to rewind the clock a bit. This whole incredible journey kicked off with a simple but really profound scientific idea. One that honestly took over a century to actually become a reality.
And it all comes down to this one concept: acoustic radiation pressure. That's the key. The whole idea that sound can physically push on things, well, that was first cooked up way back in the late 19th century by a physicist named Lord Rayleigh. Now, he just had the theory, but today we're actually doing it.
Okay, so let's get into the nitty-gritty. How exactly does sound make things float? How do you turn a sound wave, something we just hear, into this kind of invisible trap that can hold something up in the air?
Well, at its heart, it all comes back to that acoustic radiation pressure. See, normally the vibrations in a sound wave kind of cancel each other out. But when you crank up the intensity a lot, they start to create this steady, consistent push. It's a really subtle force, but it's powerful enough to be the foundation for this whole thing.
So here's the really clever part. To create a stable trap, engineers don't just blast sound at something. No, it's way more elegant. First, a transducer shoots out a high-frequency sound wave. Then that wave hits a reflector and bounces right back on itself. The magic happens when that outgoing wave and the reflected wave interact with each other. This creates these super stable, high-pressure spots, or nodes.
And that's the trick. Objects literally get trapped inside these sound pockets, totally defying gravity. You can think of it like being held by invisible tweezers. The object is pushed from all sides into these quiet, stable zones, and it just hangs there, completely suspended.
All right, so this isn't just some cool lab trick. Now that we've got the how down, let's talk about the why. This technology is already out in the real world, changing entire industries and solving some really big problems. And the applications are, well, they're all over the place. For material handling, you can assemble tiny, delicate microelectronics without ever touching them, so there's zero risk of contamination. Or what about containerless processing? You can actually create brand new alloys and glasses by melting and mixing the ingredients in midair. And then there's the biomedical side of things, where the precision you can get is it's mind-blowing.
Yeah, and this is where it gets really wild. We're talking about assembling human tissue, cell by cell in midair. Seriously, just picture it, building replacement tissue, maybe one day even organs, without any physical structure holding it together. Acoustic levitation is making it possible to assemble living cells into complex 3D patterns. This is absolutely revolutionary stuff.
But of course, no technology is a silver bullet, right? As powerful as acoustic levitation is, it's not perfect. There are some pretty big challenges and trade-offs that engineers are still wrestling with.
So let's look at the balance sheet. On the plus side, the advantages are huge. It's totally non-contact, which means zero contamination or damage. You get incredible precision, and it works with all sorts of materials. But on the downside, it takes a ton of power, especially for heavier stuff. Keeping things stable can be a real challenge, the equipment is still pretty expensive, and all that sound energy can generate a lot of heat you have to deal with. Okay, so what's next? Where's all this heading? Let's circle back to that amazing idea we started with, the floating factory, because it's getting closer and closer to being a real thing.
The next wave of innovation is all about getting smarter and smaller. We're talking about AI control, where machine learning will automate the whole process, making it way faster and more reliable. We're also seeing miniaturization, integrating this tech into tiny lab-on-a-chip devices. But the real game changer? It's something called holographic acoustic tweezers. Instead of just one sound trap, imagine creating a complex 3D field of thousands of them, all moving thousands of tiny objects at the same time. That's how you build a floating factory.
So what's the big takeaway here? The floating factory isn't just about making things float. It's so much more than a cool party trick. It's about a fundamental change in how we build things, how we interact with matter itself. It's about building the future piece by tiny piece without ever having to touch it.